Hey chemists, in this crash course we're going to look at the top things you need to know about KSP and complex ions, things that you might see on the AP exam. KSP refers to the equilibrium that's associated with what happens when ionic salts dissolve. So let's say we have something like lead-2 iodide. We can write it as an equilibrium becoming lead-2 ion and 2 iodide ions. And if you remember your solubility rules, that's actually a fairly insoluble, not very soluble salt, so there would not be a whole lot of aqueous ions compared to how much lead iodide solid you could put into solution. We can write an equilibrium expression for this. Same rules as what we use for other equilibria. Products, Pb2 plus and I2 minus, I minus, each raised to their coefficient, so I minus squared. You only include things that are aqueous. You don't include that solid lead iodide. So that's your entire expression. If we don't know what those concentrations are, but we want to find them based on a given KSP, you can substitute what's called a molar solubility. We'll use x for the thing that has a coefficient of 1, and 2x for the iodide in this case, because there's 2 of them, and you also square it, so you get 4x cubed. And x is what's called the molar solubility. They use that language a lot on the AP. It really just means the molarity. How much of this solid becomes the ions. So what you define as x, and they use different variables for this, but it doesn't matter as long as you know what it means. What we define as x in this case has a coefficient of 1, as does the original solid. So that's the molar solubility. What else can we say about KSP? Well, normally we look at small KSPs. So if KSP is small, remember what that means. It's relatively insoluble. But you certainly could talk about the KSP related to things that are very soluble. And then it would have a large KSP. That's relatively soluble. And lastly, quantitative thing to talk about is that it's related to delta G. The solubility of a substance is really about the free energy of that substance. And delta G, if you remember, is equal to negative RT natural log of the equilibrium constant. Here, it's the solubility product equilibrium constant. So delta G can be a measure of KSP, which is a measure of solubility. So that's about it for the quantitative stuff you'll see with KSP. Speaking of solubility, let's look at what happens when a salt dissolves on a more qualitative scale, and something that comes up quite a bit. Let's use a different salt. Let's talk calcium chloride, a very soluble salt. And when calcium chloride dissolves to become calcium ions and chloride ions, if we for a second thought that these were gas phase ions from the original solid, the reaction you have in front of you is actually the opposite of the process that's associated with the lattice energy. Lattice energy is defined as the amount of energy released when gas phase ions go into the solid state. It's released, so it's a negative value. This is the opposite of that. That means this is an endothermic process. We are breaking the ionic bond between the calcium and the chloride ions and sending them into the gas phase. We don't actually get them into the gas phase. They go into water. So they mix with water molecules plus H2O. And they form special interactions with those water molecules. Remember, if you have a calcium ion and a nearby water molecule, the more electronegative oxygen atom of a water molecule will orient itself closer to the positively charged calcium ion, and vice versa for a chloride. The less electronegative hydrogen atoms will orient themselves toward the chloride ions. And you can even draw little dotted lines to show those interactions. These are called ion-dipole interactions. And they're kind of like intermolecular forces, but they're not between molecules. Ion-dipole interactions. They're between an ion and a polar water molecule. And that's an exothermic process, the formation of an attractive force between a solvent and an ion is exothermic and it releases energy. So how much energy is associated with when you dissolve a salt is the combination of the endothermic and the exothermic processes. In fact, this isn't even complete we also have endotherms associated with water molecules just separating from each other to make space between them. That also has an endothermic process to get them to be farther apart. So delta H is the sum of the endothermic and the exothermic processes. Sometimes there's more energy absorbed, and therefore it's overall a positive delta H. Sometimes there's more energy released, and there's overall a negative delta H. It depends on the salt and how favorable or unfavorable those interactions are. Okay, so that's a quick crash course. Let's look at some practice questions, starting with a couple of multiple choice. The first one is sort of related to KSP. It says we have the dissociation of calcium fluoride. If you remember your solubility rules, that's very insoluble, so KSP is very small. And they want to know what's up with this graph of pH versus the calcium ion concentration. Looks like as we lower the pH, the calcium ion concentration goes up. Let's actually explain why that makes sense. Whether or not we need it for the question, I'm not sure yet, but let's write out the dissociation and remind ourselves of a couple of things of how pH can affect solubility. So as pH decreases, remember that means the H plus ion concentration actually increases. So we have to think about what H plus can do to either of these ions. In this example, you can form HF, which is a weak acid. And anytime you form a weak acid, that means that the ions actually combine and stay as a molecule. So adding H plus ions to this equilibrium removes fluoride ion from this equilibrium. That perturbs the equilibrium and forces it to go more forward, hence the calcium ion concentration increases. So calcium fluoride is more soluble in acid because you form a weak acid. If you look at the choices, the only one that even comes close to that, and you didn't even have to know all that to get it correct, would be C, because it simply makes you interpret the graph. At a lower pH, the calcium concentration is higher. None of the other choices even say that as a true fact. It happens to also have a correct explanation. I could certainly see them using this as a free response question somewhere else, and they're almost giving us a hint as the kind of wording they like to look at. That's a good tip when you're studying for this. Look at the multiple choice questions very carefully. They're not making that wording up. They're actually giving you exactly the kinds of terminology that they want to see from you on the free response questions. Let's look at another multiple choice first, and then we'll eventually get to a free response. Here we have a couple of reactions with K values, and they want to know what's the unknown K. How do we get K3 in terms of these two other K values? For this, I'm going to first think about Hess's law and what I have to do to these first two reactions so that once I add them together, I get the third one. Well, if you keep the first reaction the same, but then reverse and double the second reaction, you'll get exactly the reaction that you want. And if these were delta H values, that's exactly what you would do to the delta H. But that's not true in this case. These new K values, we take those factors we just figured out, those become the exponents. So the first K gets raised to the first power. In other words, it doesn't change. The second K gets raised to the -2. In other words, you square it and reciprocate it. If you need a refresher as to why that's true, go back and write out the expression for KSP for this silver chloride dissociation, and then write out what it should be when you flip the sides of the reaction and double it. You'll see that it has to be squared and reciprocated. So K3 is equal to the product. Once you figure out how the two reactions add together, you multiply their K values. So this becomes K1 times K2 to the -2. And then be careful when you look at the choices. The correct choice actually doesn't have the negative in the exponent. They made it positive. So I'm actually dividing by the second K2, which makes D the correct choice here. Okay, one more multiple choice. It's another KSP question, this time about mercury 1 iodide becoming mercury 1 and 2 iodides. They tell us that the solubility or the concentration of iodide is 4.610 - 10. They want to know the KSP and the molar solubility. Well, the molar solubility is sort of the X value. It's going to be KSP is equal to, there's 1 mercury and 2 iodides, so X times 2X squared. We actually know what 2X is. It's this 4.6 times 10 minus 10. So that means X is half of that. So I'm looking at either choice A or C, just in terms of the correct K expression. And then the molar solubility is X. So only choice C has the correct answer. They're using S instead of X. It's the same thing. They're just calling it a different variable. Okay, let's wrap up with a free response question. This one actually happens to have a complex ion in it, which we haven't seen at all in this crash course. It's because complex ions really aren't on the AP that much. The only thing I think worth knowing is that you'll see them sometimes, and they have really big K values. They're usually very favorable to form. It says we got a polyatomic ion, and it forms complexes with barium. They give us a volume and a molarity of that ion. They give us another volume and a molarity of the barium, the other reactant, and it combines to make a 100 ml solution. Considering the value of K, what's the concentration of the barium complex ion in the solution? I'm really noticing this considering the value of K part. I gotta somehow comment on it. Aha, K is really big, so that means this reaction essentially goes to completion. So I don't even have to treat this as a equilibrium style problem. I can treat it just as a regular stoichiometry problem. I'll rewrite the reaction. Barium plus EDTA, 4 negative, becomes the complex ion. You don't necessarily need to do this for a complete right answer, but good way to just keep track of stuff. If I look at what's up above, we have 50 milliliters of a 0.2 molar barium solution. That's 10 millimoles. Remember, when you multiply molarity times milliliters, you get millimoles. How much of the EDTA do we have? We have 50 mils as well, but if I look back, it's only 0.3 molar. So this is a limiting reactant problem, and the 15 milliliters, millimoles of the EDTA is excess. So we lose all the barium. We lose a stoichiometric amount of the EDTA, which means I have 5 left over. But most importantly, we gain 10 of the barium complex ion. That's from my mole to mole to mole ratio, which is 1 to 1 to 1 in this case. It's kind of like a rice chart. I'm just using it to track the stoichiometry of everything. So, in terms of the value of K, because K is big, the reaction goes to completion. And the concentration of this complex is a molarity. Remember, molarity is moles per liter, or millimoles per milliliter, which is the sum of the two in this case. So it's 10 divided by 100, which is just 0.1 molar. I doubt they would grade for sig figs, but I'll bet their answer key has 2 sig figs because of the 2 sig figs and the molarities given. Okay, last question. Then they dilute it with distilled water, so the total volume is a liter. It went from 100 mils to a liter. It's much bigger. After equilibrium is reestablished, what happens to the moles of barium? Is it greater, less, or equal to as what was there before? This is sort of a Le Chatelier's principle question, but it's a little more quantitative, and for this I'm going to refer to Q. Remember, Q is the same as the expression for K, but it's prior to reaching an equilibrium state. So let me write the expression for the equilibrium constant. That's the bracket barium EDTA 2 minus anion times bracket barium ion times the ligand EDTA 4 minus. And that has some value, big number, 7.710 to the 7. we diluted it. We diluted it from 100 milliliters to a liter. So every single molarity was diluted. So every single molarity was cut tenfold. So I'm going to put times 10 next to every single one of these expressions. That's actually what happens. That's our Q expression. How does this compare with K? Well, if you simplify, you get this expression times a tenth divided by a tenth, and then another tenth in the numerator and the denominator. That means you get 10 times the equilibrium constant. So Q is larger than K. And here's a good point to remind ourselves of a little trick. When you're comparing Q with K, I always like to write K first. So in this case, K is less than Q. And when you write it that way, it makes an arrowhead. So it reminds you which way the reaction responds, as long as you write K first. So this reaction is going to respond by going to the left, because Q is larger. We could go into more depth about why that is, but that's just a quick trick. So if this goes to the left, we are increasing our moles of barium ion. So we'll say because K is less than Q, the equilibrium shifts left and the moles of barium increase. It's never a bad idea to box the most important part of the answer. That's probably the first thing they look for. Make sure you answer the question first. Greater than, less than, or equal to. Actually, I didn't. I said increases. I should actually change that to use the correct wording. I'm sure they would give me credit, but the moles of barium is greater. That's the word they're going to be looking for. Okay, so that's a couple of practice questions, mostly related to KSP, that will hopefully help you in this crash course.